so much. Yes. All right. So thank you for having me here. It's a great pleasure to share one of my sort of the projects, right? Identifying marking structure, a deep network representation learning of using social engagement data. So this is joint work with Yi Yang from HKUST and also the PK Kanan from the marketing department here. And I would like to have this talk more interactive. If you have any questions, I mean, whether it's the clarification questions or harder or deeper questions, please interrupt me. So first, I want to explain why we're gonna study this topic, right? Identifying market structure. This is the well-known, well-defined research topic. Has been studied for many, many years, right? And then once we get into the literature, you're gonna find the evolution of the literature in this domain. And then why we're gonna study sort of the competitive market structure, right? Let's say studying competitive market structure can help us understand the extent of competition among brands. It can also identify the sub-markets or the market, right, where the competition comes from, right, within a sub-market or within a market. So the idea of identifying market structure is, given a focal brand, I want to identify the brands in the market that compete very closely with it as compared to other brands. So that is the general or the broad definition of market structure. So there are lots of research has been done, as I said, in the domain to study or identify market structure. It goes back to 1980s, right? At that time, the researchers was using the panel data of consumer purchases, right? Based on the consumer purchase, the product purchase, they can calculate the brand similarity, especially using the purchase switching data. And then once they calculate the brand similarity, they can cluster brands into different groups, right? They can also cluster brands at a different level using hierarchical clustering, and then for market structure identification. So this is one of the typical sort of the technology. They use the subset selection. It's called consideration subset selection technology, right? So they have the consumer purchase behavior or the data, the product purchase. And then from the consumer purchase behavior, they can identify the brand switching from which brand to what brands. And then based on the switching sort of the data, they can identify the subset for every brand that can guarantee a probability of correct selection for at least for some probability for the market structure identification. As I said, this research topic has been there for many, many years, right, since 1980s. So at the very beginning, researchers was using survey data. For example, they can send surveys to the participants to solicit the brand similarity, right, or the relationship among brands. I mean, you realize that this is not efficient, and also it's lag behind, right? And then later on, researchers have been using scanner panel data, right? And then as the clickstream data becomes more popular, researchers have been using clickstream data. In addition to those consumer behavior data, they also incorporate marketing mixture data. For example, the advertising spending or the customer segmentation or customer characteristics, right? So in the area context of big data, right, lots of user-generated content has been sort of emerging. And then researchers try to incorporate those data into the market structure identification literature. For example, researchers have been using online search logs, right? They also use the user-generated content like consumer reviews, and then forum discussions, and then social media chatters, as well as the image hashtags to try to identify the relationship among brands. More recently, in 2019, so the Gabor used the store level sales data. They consider each transaction as the basket of products. And then they use the word embedding like techniques to identify the brand or the product similarity for the market structure identification. Right, so this is to summarize the comparison among different types of data. As you can see, for some data, let's say primary data, the size typically small, right? For the social tagging or the search data or text mining based user-generated content data, they are typically large. And then some data are more noisy as compared to other data, maybe more authentic, right? And then some of the data doesn't have the privacy preserving, while others do have privacy preserving, right? For the search data, if you want to get the search behavior of users, you have to insert or plug in some tracking sort of the applications behind. And then you can also see the data availability of various for the social media or user-generated content. They are publicly available, like customer reviews, Facebook comments, Twitter tweets, right? But for the primary or the survey data, it's not easy to collect. And then for different types of data, it requires us to use different technologies to process the data, right? It imposes the different sort of the cost. So for the social engagement data we study in this paper, we try to minimize this processing cost. We just use the raw network data. I mean, this is a table to summarize the comparison among our study, between our study and the prior study in terms of different dimensions. For example, the objective, right? Our objective is to propose a network representation learning framework for market structure identification. And then as you can see, the size of the brands we study is much larger than the prior study. And then the number of the unique consumers in our data is close to 26 million, which is large. And then we use the data that is publicly available from online social media platform, Facebook. And then the methodology we use is the network learning as compared to the text mining used by other or the traditional or prior studies. And then when we identified the relationship between brands, we allow them to be asymmetric, right? It's not symmetric. And then it also allows a dynamic relationship, right? So as time goes, the relationship among brands changes or evolves. We provide the traditional quantitative evaluation for our proposed method, as well as some additional validation, like event study, okay? We're gonna see that in details. So given the proposed methodology, we expect this can handle large scale, easy to obtain data, and then it can learn complex and implicit patterns from data, and then it can identify submarkets without pre-specifying boundary, which is the big difference from the prior study. Most of the prior study, when they do market structure identification, the first thing they do is to specify the domain, right? Or which industry, which category. And then they're gonna do market structure identification. What we do here is we let the market structure emerge from the data. We don't have to pre-specify any boundaries. So the relationship among brands can across different categories. So let's say one of the brands is very close to a particular brand. They are not necessary to be in the same industry or in a category.
Okay,
so we also want.
How do you define the connection in your network?
So you're going to see that in a minute. I'll explain how can we construct the network using the social engagement data. Yeah.
Okay.
Okay. And then we also expect our method can capture dynamic changes of market structure. So the data we're going to use is from social media platform like Facebook, right? There are lots of engagement interactions between users and brands. For example, you can like a brand or you can like the post from the brands. You can also make comments on the post by brands. You can share their post, right? So the nature of this data, it's more like a high-level brand metrics as compared to SQ level. And then we wonder, is this data useful? Can we use this data to identify or to mine in some insights? Why are we going to use the likes? Why are we going to use the comments from social media? Right? The historical sort of this study showed us that 90% of the users on Facebook said that they like at least one brand on Facebook. And then 50% said that the brand's Facebook page is more useful than the company's website, right? And then among those Facebook users who like brands, so most of them say Facebook is a good place to interact with brands, right? They feel like more connected to the brands on Facebook. And then 69% said that they like the brand because a friend in their network like the brand. Why do they like the brands, right? It could be various reasons. For example, they want to get the coupons or discount from the brand, right? Because their friends like the brands, or because they want to support the brands, because they want to share their personal experience with the brands, right? Or because they want to research the brands when they're looking for specific products or services, right? Or especially when they like multiple brands, it could be have some implicit relation among those brands. And then you may wonder, do like translate to purchase, offline purchase, or to convert the users into the loyal customers? So it has both sort of the sides, positive and negative. But the prior literature has shown that the likes can be translated, projected into some positive impact or the marketing outcomes. Therefore, in this study, we think we're going to use the social engagement data, especially likes and comments, in the network analysis to identify, to extract the latent semantics among the brands for subsequent analysis, especially for market structure identification. So here's the overall framework. It has 4 steps. The first one is data collection. I'm going to explain to you what kind of data we're going to use, the details of the data. And then the second step, once we have the data, we're going to construct a heterogeneous network. I'll explain how we're going to construct this network. Basically, we're going to have 2 types of nodes. We have brands, and then we have users. And then we only have links or edges between brands and users if the users and brands had some interactions. For example, the users like the brands, or users liked the post, or made a comments on the post by brands, or share the comments by the brands, or share the post by the brands, right? Those kind of the interactions. And this is the directed and weighted network. I'll explain how can we construct those weights later, undirected and weight. So once we have the network, and then we're going to use the latent representation learning in the deep learning domain, right? It's called the deep autoencoder. But the deep autoencoder was designed specifically for image analysis at the very beginning in the computer vision domain. Since our data is the unstructured network information or network data, we're going to change a little bit to make it deep autoencoder adapt to the network representation learning. So basically it projects every node in the network into a low dimensional representation. We can consider them as vectors, right? While preserving the structure and semantic information within the network. Once we have that is the step 3. Once we have the vector representation for each node, we can identify market structure. We can visualize. For example, we do dimension reduction, right? Further dimension reduction. We can do lots of sort of the studies using those vectors. To give you a sort of the intuitive idea, what is the deep autoencoder, right? As I said, it was designed in the computer vision domain. So it says, given an image, it can compress that image. So this is the better. So let's say given an image, it can compress. They have 2 components. One is called the encoder. The other is called decoder. So they're going to use the encoder. By the way, the encoder and decoder are realized by neural networks. It's the function, just the function. So given an input, so through the encoder, it becomes a vector. Usually we call the bottleneck. It's just the low dimensional representation is a vector. For example, it's a 300 dimensional vector or 128 dimensional vector. And then that bottleneck or that vector can be used as the input to the decoder and then used for the original input reconstruction. So the basically says we compress the data into some lower dimension representation, which can preserve most of the information of the original data, because that representation can be used to reconstruct the original information. So, but all this transformation, encoder and decoder, are non-linear. I'm sure most of you guys are familiar with PCA, principal component analysis. If you compare, they're very similar. It's the dimensional reduction, right? If you put the PCA and deep autoencoder together, they're not that different. The only difference I would say is PCA is linear dimension reduction, while the deep autoencoder is nonlinear dimension reduction. All right, so now let me show you what kind of the data we're going to use. So we use the Facebook, as I said, right? So first, we're going to identify the top list of US brands based on the number of the followers from the socialbakers.com. And then on the socialbakers.com, so each brand of Facebook brand is categorized into one of the 25 categories. Right? For example, could be brand, could be celebrity, could be a community, entertainment, media, place, society, and sports, etc. So our focus of this paper is on brands. Right? For example, Walmart, Amazon, Target, right? Those are the brands. We don't consider any celebrities. We don't consider any sports teams, right? It's the brands.
KZ, yes. I have a question from the audience. So why do you only consider the connection between the brands, not the connections between the users?
Good point.
So doesn't the user information contribute anything for the model?
Yes, yes, absolutely. Absolutely. If you have, so let's say if you have the user friendship or user network, definitely it can improve, it can enhance the model. But one of the sort of the advantage I didn't mention is the privacy preserving, right? We don't have the user friendship network. Oh. We don't have their private sort of the connections. So we only have public available data as the user brand interactions. If you have user network, user connections, or the brand connections, definitely it can improve the performance, right? Which we have already observed that in our another project, we have sort of this information. But for this project, we do not have the user connection data.
Thank you. Thank you for the explanation.
All right, and then we're going to use the Graph API, right? It's the Facebook provided to collect the user or user brand interaction, including the posts, the text information from the brands, and then the comments, and then the likes from the users and shares from the users. So, and then for this analysis, we just use 1 year, but actually we have collected more than 20,000 different types of brands. In our database, and then for every brand, so when I say 20,000, it's not only just the brands, it also includes the celebrities, communities. But for this study, we only focus on brands, right? In our backend database, we have more than 20,000 different types of Facebook public page information. And then for each page, we have everything from the first day they found it on Facebook until April 2018. Because after April 2018, Facebook Graph API becomes limited, right? It's as long as you become the partner of Facebook, they open the API for you to download their data, right? Because of that Cambridge Analytica sort of the event, right? And then for this study, we only use 1 year data, 2017, because we think that data wasn't affected by any sort of the leaking information. And then we focus on the brands, Facebook pages, right? And then we end up with about 5,000 brands. As you can see, the total number of the user brand interactions is about 106 million. Once we have the data, we have to clean the data, right? To improve the quality of the data. We did a very simple, just rule-based data cleansing. We follow the previous work. For example, one of the rules is if a user engaged with many different types of brands, for example, a user make comments on more than 500 different brands, which is possible, but it's very low probability. We consider this user might be bot, right? So suspicious users, we remove them and their corresponding sort of the activities. All right, so now let me explain how can we construct this network, right? We have users and then we have brands. It's more like a bipolar graph, right? We don't have the connections among brands. We don't have the connections among users. So we only have connections between user and brands. And then it is undirected and it's also weighted. So the weight of age between a user and a brand is the frequency or the number of the times the user engage with the brand. By the way, we do not distinguish likes, comments, and shares. By the way, we did not use the shares because the share, at that time, we couldn't get the individuals who shared the post. We can only get the total number. But then Facebook changed their policy. All right. So the objective here, once we form a network, so the objective here, we want to project every node in the network into a latent space, right? Or let's say 300-dimensional space or 200-dimensional space, it's the latent space. But we don't want to lose the original structure or the semantic information. We want to preserve the local and global network structure information, as well as the semantics. When I say semantics, for example, the weights, right, between the users and brands. So the objective here is very simple. We try to minimize the total loss. And then this total loss consists of three. We're going to explain. So the first order similarity, the second order similarity, and also the reconstruction error. So what is the first order similarity? So the first order similarity is more like a similarity to neighbors. It is a local pairwise similarity between a user and a brand. So it says, if a user and a brand has a connection and their age weight is large, then we say there's similarity in the projected space, right? So let's say for the user node and brand node, in the projected space, they should be close to each other because they are similar. That's what we call the first order similarity. And then the second order similarity is the similarity to neighbors of neighbors. Let's say given, for example, two brands, they don't have connections in our setting, right? But what if, let's say, two brands share lots of common users? So they should be close to each other in the reduced dimensional space or in the latent dimensional space, a projected dimensional space. This is what we call second order similarity. And then the third one is called reconstruction error, right? So we try to minimize the reconstruction error between the length representation and also the original representation, because we want to preserve the information, the global information as much as possible, right? It's more like compress the nodes or the network, and then we can use that representation to reconstruct the original network. That's what we call reconstruction error. We put them together, that is our learning objective. So once we get the representation for every node in the network, so by the way, what is the vector for every node? It is the output of the case layer. It's the last layer of the encoder. So we use the encoder and decoder. So it is the last layer of the encoder, right? That is the output of each, it's the representation of each node, whether it's the user node or the brand node. And then let's say it's the 300-dimensional vector. Once we have this vector for every node, then we're in the familiar territory. So we can do lots of subsequent analysis. For example, we do clustering, we do visualization, we want to see the market structure, right? And then for the visualization, because we cannot visualize 300 dimension, we reduce the dimension into, let's say, 2 or 3 dimensions. We're going to use different technologies. In our paper, we try different techniques, t-SNE, UMAP, or PCA, right? And then we say, we find the t-SNE performs similar to UMAP, which give us the sort of the best results. Okay. How do we evaluate whether the method you proposed here, it's called the deep network representation, is reasonable or is good, performs better than the baselines, right? So to evaluate, we face several challenges. So the first one is we don't have ground truth. We don't know, let's say, suppose we learn the representation and then we do the clustering and then we found the brand 1 and brand 2 are together very close. Or we say they are, so this is the market structure, right? They are very close. They are very far away from another, let's say brand 3. How do we know this is correct? Because we don't have the ground truth, right? And then you may say, can we use the industry classification? For example, the standard SIC, standard industry classification, or any North America industry classification, right? Yes, you can, but it's limited because they are static. They don't reclassify firms over time. So then we think, can we find an alternative evaluation, right? Instead of using the ground truth or the industry classification, can we find the alternative evaluation? So the key here is, if we have a good brand representation or the user representation, right? Then everything learned from that brand representation should be good. That is our assumption, right? The good representation of brands will give us good output, which are based on their brand representation. So we think we're going to use the link prediction, which is the commonly used evaluation procedure in the computer science domain for network representation learning. All right, so what we did is we split the data into, it's more like training and testing, but here we call it the representation learning. We use the first half of the year, the data as the representation learning, and then the second half as the testing. So what we did is, during the first half, we construct the network, the heterogeneous network, and then we learn the representation. That means we learn the vector representation for every node, brand node and user node. And then we randomly select some amount of users. Let's say for every random selected user, using our algorithm, we can predict what are the users, sorry, what are the brands those users will connect to during the testing period. And then during the testing period, we're going to verify how many of the predictions are correct, right? And then we're going to use the standard precision at N or precision at K or recall at K to evaluate the link prediction or this algorithm. So we have some baselines. So for the baselines, we have a 2x2 design. So first is network, and then we have heterogeneous, which is our user brand network, right? And then we also, from the user brand network, we can also construct the homogeneous brand network, right? And then for the model, we have shallow and deep. Let's say we're going to use the matrix factorization. We have user brand metrics, right? So each cell within the matrix is the frequency of their interaction. And then we have our deep autoencoded representation learning. So this is already. So now let's look at, so first we're going to randomly select 100 users. And then for every user, we predict, let's say 10 links, top 10 links, top 100 links, top 500 links, right? And then we're going to see during the testing period, any of these 10 links is covered or occur. If it occur, we say that is a hit, right? If none of these 10 links occur, then it's not, that user is predicted in the wrong way. And then we count how many times. This is what we call precision at K or precision at N. This is for the precision. And then similarly for the recall, this is for randomly selected, 100 randomly selected users. We also increase the size. Let's say we do another 1,000 randomly selected users. As you can see, our model is better than those baseline models. And then what about the training size? Is there any impact of training size on the performance? And then we try, let's say we're gonna use 10%, 30%, 50%. And then you can see as the training size increases, so the performance increases, but once you reach 90%, it doesn't change that much. This is the recall. And then for the network we constructed, right, we use both comments and likes. And then for the comments, we don't distinguish it's the positive comment or negative comments or neutral comments. We do not, we just consider them as the engagement. And then what if, let's say we separate likes and comments? We just use the like only to construct the network. We just use the comment only to construct the network. So, and then you can see it's also performing better than the baselines. This is more like a standard evaluation. It's from the link prediction perspective, right? It's the alternative evaluation, it's the quantitative evaluation. But our final objective is to identify the brand relationship. It's the market structure, whether these two brands are similar in a close position in a structure, in a brand sort of the map, right? And then we did some extra validation. So the one is we're going to use the Amazon Mechanic Turk, the crowdsourcing platform. Let's say we choose one of the domains called auto domain. In our data, we have 28. The original data set, we have 28 for this study. We have 28 auto brands. And then from those 28 auto brands, we construct 28 by 28 metrics. And then each cell within the metrics is the brand similarity. First, we're going to ask Turkers in the crowdsourcing platform, we ask users to rate the brand similarity. For every brand, we're going to give a set of the brands, ask them to rate, give the rate. And then we calculate the brand similarity. That is from the crowdsourcing platform. And then we also use our learning-based method to calculate the brand similarity. And then we calculate their correlation. For these two matrices, we calculate their correlation. This is the first sort of the validation. And then the second one is we're going to use the Google search interest score, right? For every pair of brands, we give the brand name and then put it into the Google search interest. And then it returns for that year, for the 2017, for that year, Google in North America. So, and then Google returns, the interest score. And then we focus on 19 airlines, okay? And then similarly, it's not a metrics. For the 19 by 19, we have 361 similarity scores, right? And then we have the scores from the Google search interest. We also have the scores from our learning-based vectors. And then we calculate the sort of the correlation. Those are sort of the evaluation. So now let's look at what we can find. What are the insights we can derive? So first, once we have the vector, we can visualize, we can do dimension reduction, we can visualize, right? Here I put every brand, right? Each dot is the brand and different color represent their different industry code. So from this global market structure visualization, we can see, I have a website, and then you can, if you're interested, you can take a look at that. It's interactive sort of the map. So we have, let's zoom in to look at this for sort of the clusters. Number one is about the auto sort of the cluster. One of the interesting finding is, if you look at this cluster, you see some of the cars right here. Those are the low budget cars. They are showing up within this cluster. And also if you cannot see it, right? Within this sort of the map, we also have high-end car brands. For example, Mercedes-Benz, we have Maserati, those brands. They are not in this cluster, but they are close to brands like Chanel, brands like Gucci. So this indicates that our net and representation learning method can not only learn the industry sort of the classification, right? Those are the cars, but also some latent dimensions. For example, the luxury, some price, right? Based on the user engagement data. It's the common user, something like that. This is for the resort cluster. This is for the airline. We're going to come back to look at this cluster. There's some interesting findings. We're going to come back to look at this cluster in a minute. And this is for the cosmetics. All right, and then we further pick, let's say, 4 brands: United, Southwest, Audi, and Nissan. Let's just focus the first 2, Southwest Airline and United, because Southwest Airline is often considered as the low budget airline, while the United is not, right? If you look at the first 2 sort of the columns, United and Southwest, there are several interesting findings. The first one is, it is asymmetric, right? If you look at the South Airline, the United is ranked in number 6. Those are the most similar brands to Southwest Airline. And those are the most similar brands to the United. And then if you look at the United, the Southwest is ranked number 4. Right. Another interesting finding is, if you look at this top 10 similar brands, they are not all airlines. If you look at this one, Airfare Watchdog, it is the deal finder for flight tickets, right? It's supposed to help you to find the cheap flights. And then if you look at this, Airfare Watchdog is ranked higher than the Airfare Watchdog similar to the United, right? Which you can, to me, it makes sense because the Airfare Watchdog is a deal finder. If you care the price, I think you might be more likely to sort of go with Southwest airline, right? Potential, just a possibility. This is just, it's also for the face validity, right? We don't, it's not a quantitative evaluation, it's just for face validity. So as I said, let's come back to look at this. We say the latent representation we learned can help firms to identify the potential opportunities and threats. Let's just look at the Hyatt right here. Right, not, as I said, this is about the airlines, but not every brand in this cluster is about airline. So the Disney Cruise Line and Hyatt are not airlines, they are hotel, they are resorts. So if you look at the Hyatt, let's say, suppose now focal brand is Hyatt. You are the manager of the Hyatt. Hyatt is close to Southwest as compared to United. And then we wonder why. Because we know Hyatt, if you look at the original data we have, Hyatt has more overlapped users with Southwest as compared to United. Similarly, for the Disney Cruise Line, has more overlapped users with Southwest as compared to United. And then Disney Cruise Line is more closer as compared to United. So as the manager of Hyatt, so if you want to, let's say, expand your user pool, right? Then you're gonna see Southwest could be a potential collaborator. You can do cross sort of the brand targeting, right? I mean, this is also be the threat for other, let's the brands. If they don't understand this, they don't, it's not an opportunity for them. This is what they could be the potential opportunities for those brands. So most of the data so far, we used, let's say 5,400 plus brands, and then user engagement. They are large brands, I would say, because their followers, let's say millions or thousands of sort of the users, right? Does your technology, so all the small brands benefit from your technology, benefit or gain some competitive advantage from what you showed here? To answer this question, we add another 241 travel brands. They are small brands. The number of the followers range from a few hundred to a few thousands. They're literally small brands. And then we put this 241 brands into the original 5,000 brands together, and then we're gonna run analysis. And then you can see those brands are predominantly located in 2 areas, as you can observe in this plot, right here and right here. And then for further analysis, we dive into this sort of the travel brands, and then you pick one brand. It's called Luxury Travel Expert. So this is the information portal for luxury travel and premium tours. It has 11,000 followers, which is considered small brands. Right? And then its most similar brands are, for example, those are the top 5 similar brands. Not all of them are sort of the travel or premium tours, right? For example, the second one, the Peninsula Beverly Hills, is the 5-star hotel. I mean, this luxury, sort of the travel premium tours is close to a 5-star hotel. And also for these 4 brands are all expert-led, small group luxury and premium tours brands. So, which further provides us a face validity. That means small brands, if we incorporate the user engagement for small brands, it can also learn with the large scale sort of the cross-category data. It can give us sort of the some sort of the observations or insights. So, and then you may wonder, for the manager, let's say I'm the manager of Target, I'm the manager of the of the Tesla. I don't have the data. I don't want to collect data for other industries. I only want to focus on within my industry. Does that work? So then we look at the within industry analysis. So let's say we focus on 163 auto brands. We put, let's say, all brands in my, whether it's the larger brands or it's the small brands, we put them together. It's the 163 auto brands. And then from this, you can see this is for all 160, and this is just one particular area. As compared to the previous, the auto cluster, that big sort of thing, right? It's less here, it's less clustered, it's more spread, and it's more ambiguous as compared to the to using the all data, right? Because we only use the 163 auto brands. We don't observe clear sort of the clusters within this auto brands. And then let's say we pick one brand, it's called FMF Racing. It is a company that develops dirty bike exhaust for off-road and racing motocross riding. And then we want to identify top 10 similar brands using auto brands only, using all brands in our data set, right? So on the left-hand side, you can see those 10 similar brands. Some of them are related to motocross riding, while like Lucas Oil or Castrol are global automotive oil brands. They're not motocross riding. It's relevant, but not that super relevant. If we use the all brands, and then we identify top 10 brands, similar brands, and then you can see those all 10 similar brands are related to off-road motocross riding. So that says using data cross-industry to learn the brand relationship based on the user engagement data give us the better sort of the results. I still have sort of about 5 to 10 minutes. I'm gonna show you 2 case studies. One is whether our technology can capture the dynamic changes, right? One is the Amazon acquires Whole Foods. That happened in August 2017, right? So let's say this is the timeline, August, let's say 2017. Before that and after that, we're gonna use data before and after. And then we're gonna calculate their similarity. Let's say for the Amazon, the focal brand is Amazon. I wanna calculate the similarity between Amazon and Lowe's, Amazon and Office Depot, Amazon and Kroger, Amazon and Victoria Fine Foods, Amazon and Walmart. And then I wanna see their similarity, the change of the similarity. You can see that since the acquisition happened, so the similarity between Amazon and Lowe Homes decreases. But the similarity between Amazon and Kroger increases, right? That says if you use the industry classification to classify, Amazon moves closer to those retailers or supermarkets, a little bit far away from the tech firms, right? Like the Best Buy, not tech firms, the retailers, the Target, the Costco, right? So it to some extent it makes sense, right? It just shows the representation learning using the engagement data give us confidence to say it's good, it works. And then the second sort of the case is Tesla derives Model 3 in July 2017. I mean, when Tesla launches Model 3, right? I mean, before that, Tesla was considered as the high-end sort of the consumption of the product. But the Model 3 is the low end. It's close to the, let's say, the ordinary, right? Lower end cars, the Toyota or Hyundai, right? And then you can see that the similarity between Tesla and those car brands, some of them are high-end, Maserati, right? And Mercedes-Benz, Audi, right? So those are the high, if you can see, the similarity between Tesla and high-end brands decreases, while the similarity between Tesla and those sort of the Toyota, Mazda, Hyundai increases. And we don't say this, right? It's going to be the trend, but at least it gives us, given the data we have during this time period, we learn some useful representations. All right, to summarize, we develop deep network representation learning on large-scale social media. It's the user engagement data for market structure identification. We add on to existing research on market structure discovery from a network analysis perspective. And then we are able to pin a large amount of brands on the market structure map to precisely visualize brand relationship. And then we showcase how this technology can be used to tackle a traditional marketing task, right? Market structure has been there for many, many, many years, since 1980s. And then this research also contributes to the understanding the market boundaries and overlaps different the product categories. It also gives us to some extent, the dynamic analysis of the changes in the market structure and boundary, right? But by the way, this algorithm is static. So we're currently working on the dynamic sort of the network, deep network representation learning algorithm. That means at the very beginning, we have a short network, at the small network. As time goes, we have more engagement added. Can we not relearn the entire network? We just update those nodes that are affected to be more efficiently learn the network representation, the nodes representation, right? And then regarding, let's say, the implications of likes and comments or shares, here we didn't sort of dive into what if, let's say, the comments are negative, or what if the comments are positive, right? What does the network give us if we only use the networks? Is that different from, we know the performance-wise they're similar, but implication-wise are they different? We don't do that. All right, that's it. I'll be happy to take any questions.
Yes, any question from the audience? Okay.